All right, so I'm going to start with an apology. In the last lecture, I spent so much time on the basics that I ran out of time and I rushed, right? So what I'm going to do is I'm going to quickly fix that and do a more extensive review and point you to where to read about to fill in the gaps, right? We can't, unfortunately, spend too much time on this. But so this is a review of the story of diffeomorphisms. Good. So we talked about, if there are any questions at any point, please ask. We talked about passive and active diffeomorphisms. The picture to have in mind is precisely this. You have a manifold, which is space-time, for instance. There's a point P. Passive means same point, two different charts, right? So physics does not depend on coordinates. So you could talk about passive coordinate transformation, which is sending x mu of p to x prime mu of p, right? Now, when we write equations of physics, we don't put the p in there. Whether it's active or passive is context, right? So from the physics equation point of view, this is nothing but x prime mu is x mu plus delta x mu. Then I have to say whether I'm thinking actively or passively, right? Now, there are the active diffeomorphisms where you have the same manifold, 2 points, P and P prime, and then one chart, right? So you map P to x mu of P. Now you talk about the physics of something happening, something that moves from point P to point P prime. That means that x mu of P goes to x mu of P prime. Again, in physics, we don't keep track of P and P prime. So what we write is an equation that looks very similar. X mu of P is x mu plus delta x mu. Good? You're with me? All right. So now, I did make another comment. In symmetries, what we're talking about, we're always talking about the active picture. For the remainder of this course, we're talking about the active picture, right? This is just for you to understand how to disentangle the two things. Good? All right. Now, in general, so this statement I just made was about moving points around. These are space-time transformations. These are diffeomorphisms, right? Now, what is a field? What the hell is a field? So I'm going to give two examples, and this is all you need to know. And I'm going to point you to reference to read about. First is a scalar field. Scalar field is a function on the manifold, right? Let's call that function phi tilde. So this is the picture to have in mind. We're in the active picture, so forget about the passive picture from now on. I only have one chart and 2 points, P and P prime. So my scalar field associates a value here, phi tilde of P and phi tilde of P prime. And I can talk about the difference, how much the field has changed as I've gone from point P to point P prime. The function has changed, right? Now, I don't want to keep track of P and P prime. I'm going to use this chart, send P to coordinate x mu of P, P prime to x mu of P prime. I just told you that this is really, what I should be talking about here is I talk about phi of x of P prime minus phi of x of P, where phi is the map that goes from here to here. So it's alpha minus 1. So it's phi tilde of alpha minus 1. So this is what phi. Every time in physics we write phi of x mu, this is the object. All right, good. Now, based on what I just told you, I told you in physics we don't keep track of P and P prime. So what do we keep track of? We call this x prime and P prime, right? So what we write is phi of x prime mu minus phi of x mu. This is a scalar field. It's a function from the manifold. It's a function on the manifold. Now, next, let me talk about something that's not a scalar field. So it transforms non-trivially under diffeomorphisms. So take the same thing. Now, instead of associating a function to each point, associate a list of functions. a couple of functions that are independent. You know, for example, take two fields. It could be a complex field, right? So consider a two vector phi1 of p, phi1, phi2 of p. Now, as I go from p to p prime, right? So I have to subtract the initial vector from the final vector from the initial vector. Here, there's room for a matrix to act on this vector. That's the story of representation. If there is no matrix act, if there's only one variable, right? That's just a scale. Good. So again, using the same notation, what we deal with, let me label these guys with phi of a. That's the eighth component of this vector. So phi of a of x p prime, which we represented with x mu, x prime mu, minus a matrix that can depend on x mu, acting on phi of b of x mu, right? Good. Now, if I want to write this schematically for the vector, right? I can think of it this way. This is a vector. The total, this is the active picture, okay? Forget about the passive. The total variation of the field is a variation due to this matrix plus a variation due to the fact that you have moved the points. Good. This is what it means to transform in a non-trivial representation. Yeah.
And then that subtraction is equal to delta, a small delta phi of x.
Small delta phi of x. Yeah. So what is this? I believe you have to first take x prime on mu to be infinitesimal related to this. You expand it, and you're going to get the structure like this. A term that's not of this form.
Yeah.
This is a term that appears only in the scalar. Now, I'm hiding something under the rug. If you see it, good for you. If you don't see it, we'll come back to this later. But if this is a convincing enough argument, you're good. But if you want to know exactly what I'm talking about, read sections 5.2 of Nakahara, Topology in Physics. It defines for you what is a scalar field, what is a vector field, what is a tensor, what are p-forms, right? It's basically this picture, a little bit more elaborate. Good. It basically tells you how you end up on those vectors to start with. I can go over it, but we just don't have time. I'm happy to go over it, but all right. So hopefully, last time I rushed it. This is a quick fix. Are there any questions? I spent too much time on the passive picture last time, and I thought I ran out of time. Good. Let's let this sink in. Yeah.
One would expect that the representation matrix depends on the target space, right?
Target space.
Depends on your choice of x, of target space.
Sorry, what is x is what? X is
target space. So you define the function phi, the field phi as a function from the
Oh, that x.
Yeah.
Oh, x. Sorry. Ask your question again. Oh,
so
of course.
The representation
Of course. Well, x. So what is x in the example I've written?
C.
No.
In the example you written, it's Rn.
Rn. Right? When the field is scalar, the function is a map from manifold to R. Right? What I wrote here is really a function that takes values in Rn. Doesn't have to be Rn, right? Good. So it's an Rn valued function, aka a list of functions that are independent and functions that are independent. Good. Any other questions? By the way, he used that X is called target space. What was quantum mechanics? Do you recall? When we said quantum mechanics of a particle, or sorry, quantum mechanics, classical mechanics of a single particle moving in d-dimensional space, is 0 plus one-dimensional field theory with d fields, what we meant was that M is R time, right? And the field takes values in RD. So classical single particle mechanics is the following field theory. Map from R of time to RD. Or sorry, or good. Any questions? So here, your space-time, in the analogy I use, your space is the target space, is the field values. In quantum field theory, this is your space-time. Well, it's your interpretation. Quantum field theory is a systematic study of those phi tildes from M to X, right? How you interpret it is really up to you. For instance, if you take M to be R1, comma 1, or R2. So I took just M right now to be R, and I mapped it to RD. I got a classical particle motion. What do I get if I take this guy, if I take this thing? Does anyone know the answer to this?
That's using conformal.
This is yeah, okay. Classical. Everything is classical, right? So it takes as an input a point in a two-dimensional space and pops out a d-dimensional thing. This is string theory. This is literal string theory. This is called the world shape. This is called space-time. So string theory is not an enormous leap from like, oh wow, like we're doing something crazy. People discovered this kind of models way before they knew about the relevance of this for quantum gravity, right? So it's a very natural thing to do. It's a very, very natural thing to do. Okay, good. Any questions? All right, so now these were the two slides to clean up all the mess from last lecture. Now we're back to life and we can talk about a high-level summary of what we discussed last time. So last time we started a discussion of symmetry, and there was a key thing that we focused on, Noether's first theorem that says if you have a differentiable symmetry of your local action, that gives you a conserved local current, right? That's Noether's first theorem. So we are in the active picture. So what is the total transformation of the field? There's a part that's internal, and then there's a part that's space-time. If it's a scalar field, there is no internal part. Then similarly, when you look at the change of the action, the total change of the action, there's a piece of it. So we did these manipulations, but at the end of the day, there's a bulk term that vanishes due to the Lagrange equations. And then there's a boundary term that's left. The boundary term, not surprisingly, has two pieces. One has to do with delta x mu, and the other one has to do with the total change of the field phi. The coefficient of delta x mu is called the stress tensor. That's the definition of stress tensor for you, right? Every local field theory has a stress tensor. I don't need to assume anything.
Not even translation.
I didn't say it's a conserved stress tensor. Okay. Right? So here's a stress tensor for you, just as a consequence of locality. Then what did we say? We said that, all right, so let's parameterize these delta x mu and delta phi a with a bunch of variables. Then the symmetry tells you that the symmetry will basically tell you that you call this the current, right? And of course, it's conserved, right? So your local conservation law is this. Now, here are a couple of examples that unfortunately, example 2 I skipped, and that will come back and bite me. I don't have time to go over it today. I'll have to squeeze it in one of the lectures. But I encourage you guys, maybe I can do it as a homework. So when I talk about phi 1, phi 2, I can also think of it as a complex scalar. That's the example. Then rotations of this phi 1, phi 2, rotation in this plane is just multiplying the complex field by e to the power by alpha. Right? Let's say U1. But that was the example. And then there's a conserved current associated with it. That's actually very important. It will help us explain antiparticles and all that stuff. But that's way later. All right, very good. So here we go. If you take, now we define stress tensor. If you take your symmetry to be translation invariant, meaning that if your action is translation invariant, what's your corresponding conserved current? It's just the stress tensor. What's the equation becomes the following. It tells you that the stress tensor is conserved, meaning that del mu t mu nu is equal, or theta mu nu is equal to 0. It has two indices, the current. I've been writing the current with one index, but that's just symbolic. There's one index that's contracted with delta. All right. So let's give example 2. If you take it to be Lorentz transformations, it's this guy. So sorry, we made a comment. If given translation invariance, you already have a conserved stress tensor, which means that you have conserved energy and conserved momentum, right? But then if you have on top of it Lorentz invariance, the full thing Poincare invariance, then to arrange for this is your conserved current, and the only way to arrange for it, well, I did not say that. One way to arrange for it is to make sure that the stress tensor is symmetric. Good? All right. A fun exercise for you guys. This is a fun but very, very deep exercise. What if your action has scale invariance? What is scale invariance? X mu going to a number lambda times x mu. What is the corresponding conserved current? Does everyone know? We'll go over this later. Yeah, but that's the charge. What's the conserved current? We'll go over this later. It becomes the following thing. It becomes T mu equal theta mu equals 0. This is the, again, it has to do with stress. So as you can see, all the space-time transformations, symmetries, put constraints on the stress. It gives you this, meaning that stress tensor has to be traceless. Good. Now, we will do this exercise, but the really interesting, fun exercise is that can you have Poincare plus scaling and not the full conformal group? So there's something larger called conformal group, right? Which is often said if you have Lorentz invariance and you have Poincare and scaling, there is a new guy called special conformal transformation that will be symmetry. Whether that's imposed on you or not is a really cool exercise. It's a good research topic in the quantum world for a while now. Anyway, so that's a detour. I'll come back to this and talk about this way later in QFT2. All right, questions? This is a summary of last lecture. Hopefully cleans up some of the mess of rushing at the end. Yeah.
And something that I can wrap my head around is those, when you say delta phi A is equal to epsilon I times phi, those epsilons are not the same when you are talking about delta phi A and
yeah, they're different, of course. Yeah.
Oh, okay.
These are epsilon is just some independent, these are independent variables. Yes, sorry, that's
okay. But they're not the generators of the
oh, sorry. Wait. Now I see what the issue is. What is the issue? The issue is that you make a transformation. Let's say you make one transformation. It has an epsilon parameter. Delta phi changes by that epsilon, this guy, and delta x mu changes with that epsilon, right? So that's one epsilon. Now, you take a transformation that has two parameters. Like, for example, you have an R2 worth of symmetries. Then there will be epsilon 1 and epsilon 2. So it is the same one in a sense.
Okay.
Right? Is that good?
Yeah. Correct.
Because, I mean, unless you have the scalar field, there's no way to separate. Well, I mean, scalar field, there's no way to separate the two transformations. You can't just transform this one. You just transform. If the field is not scalar, you can't just transform delta x.
Okay.
Yeah.
Can you say again what the capital phi mu i's are?
The coefficients of that transformation. How does the field change?
So is it arbitrary? It's just up to our choice?
It's a representation.
It's representation.
It's the content of the. So for example.
And then that representation affects what our current is.
Exactly.
Okay.
Exactly. Absolutely. So for example, you are familiar with this, but you might not have seen it this way. Well, okay. Yeah. No, that's a choice of representation. If it's a scalar field, it's always zero. Those guys are always zero. Okay. But if it's not a scalar field, then you'll pick up.
I see. Thank you.
Sure. Any other question? All right. So today, finally, we get to today. So we said that there is this triangle which had three parts, right? I had by not writing it. I had differential symmetries. Here I had conservation laws. Here I had the Lie groups and Lie algebras. Today we're gonna go this way. They're all related, right? So today we're gonna start with differentiable symmetries and connect them with Lie groups and Lie algebras. Here is probably the only time, and before like part 2 of the course in quantization, I quote something quantum mechanical. It doesn't really have to be quantum mechanical, but I'll quote Wigner's theorem because it's just so good on point. All right. So the same way that connecting differentiable symmetries to conserve currents involve the theorem, Noether's theorem. Here, there is a theorem that connects differentiable symmetries to Lie groups and Lie algebras, and that is Wigner's theorem. Ish. This is, so I say the word quantum here. So Wigner's theorem is a statement about the Hilbert space. Technically, I don't even need to say that. It's a little bit tricky because of, for the purpose of this course, I'm going to say this. All right. Wigner's theorem at the end of the day is a proof in math. It's a mathematical statement. It's about the way you interpret it that involves quantum mechanics. All right. So today, what are we going to go over? We're going to go over what is a group, what's a group representation, and what are the examples of important differentiable groups. Pretty much the list of, unless you end up doing some hardcore group theory in high energy physics, by the end of this lecture, we're going to discuss all the Lie groups and the algebras you'll probably ever encounter in physics. Unless you do some serious exceptional groups. I've never done it. So I'm just basically summarizing everything I know. Good? All right. So is it clear where we're going today? So first statement, this is symmetry transformations form a group. What does that mean? Well, take an example. Let's work out an example. Take Poincare transformation. A particular Poincare transformation could be labeled by two things, a translation vector and a Lorentz transformation matrix, right? So this is an element I'm going to call G as the compact notation. It's one particular Poincare transformation. So I have a symmetry if I have a function. So let's just make it even more abstract and think of symmetries in the following sense. I have a function of x, s of x, that g acts on x. The function is invariant under the action of g. So s of x is equal to s of x prime.
At the bottom, is that G1, G2?
G2 or G2, G1?
Oh, that's, yeah, I think G1, G2. So now it follows immediately that if you have two transformations of this type, the multiplication is also symmetry. If you have two symmetries, two symmetry elements, the multiplication is a symmetry. So you can multiply. Multiply means, apply this one first and then that the other one. The order might matter. However, the symmetry transformation remains a symmetry. Good? All right. So there's a natural notion of multiplication between these transformations. There's a notion of inverse, which is you do a transformation that sends G1, and you could do a transformation that undoes that. Right? This is G minus 1. It's the two, or another way of thinking about it is two transformation. You do a transformation, and then the question is, what is this transformation that you have to follow it by with so that the net result is identical? And that's called G minus 1. Any transformation you do could be undone. That is sort of the symmetry. Every symmetry transformation could be undone. All right, that's already all the criteria to get a group. So there you go. That's why we talk about groups. What's a group? It's a mathematical construction of this, like this. It's a bunch of G's. It's a set of G's, G1 to something, with a multiplication operation. Only a multiplication operation. There's no addition. So for all G1, G2, G1 and G2, G1, G2 is inside the set, so it has to be closed under it. The multiplication is associative. It's pretty clear what it is, right? There exists an identity element, and then there's an inverse. That's a group. It's very important that associativity is very important. If it's not associative, that's kind of crazy. It's rich, but we're not going to be talking about it, right? So for example, rotations. Have in mind rotation. Rotations, of course, are associative. Matrix multiplication is associative. Good? All right. Now, so that's a group. What the hell is a Lie group? Lie group is a differentiable transformation that forms a group. It's a differentiable group. It's a setup where G's are not a discrete set. They are sort of a continuous, the label G is continuous, so that you could take derivatives.
That's also a group. Or
Lie groups are manifolds, yes. But there are extra criteria. So this is a colloquial, right? So it's a differentiable, but has a little bit more than that. It's not just differentiable. So Lie groups, that's why I said colloquially, are definitely differentiable groups, but they have more structure. So there is such a thing called group manifold. It's not hard to imagine what it means, right? And Lie groups are special cases of group manifolds. Now, already, you should have an interesting thought in mind that when you have a space-time or space, you could view it as a group, right? We'll see later that these groups we're talking about are they correspond to, well, sometimes they correspond to internal transformations, right? So there is a nice interplay between internal and space-time. The space-time is also could be used as a group. Somehow already used that in a lot of so there's a nice interplay as what is internal, what's not internal, what's space-time. I've already used that in this analogy of the fields being the correspondence with particles. All right. So if that's confusing, ignore it for now. So space-times that are very, very symmetric, there would be some of them end up being Lie groups.
Are all differential groups?
No. No. This is colloquially, so I haven't defined it for you yet. Right? So not all differential groups are groups. So on top of it, you need a notion. All right. So examples. I will actually, for that, if you want to see the definition of it, I don't think I'll define Lie groups here. Maybe not today. Maybe next lecture I'll define it. But if you want to know exactly how it relates with a general differentiable group, Nakahara. That's my suggestion for all of these kind of. Nakahara is like topology, physics, and topology, geometry, and physics. It's a blue book. It's very clean. At least this section of it. Don't ever read the connection part, gauge theory part. It's incomprehensible. But I'll try to do a good gauge theory discussion, but in QFT2. All right. So example. The simplest example is S1, a circle, right? So the elements we're talking about is a rotation of a circle, right? The transformations then send theta naught to theta naught plus theta. Theta here is an element of the group, right? You could multiplying two of the elements of the group is like adding theta 1 and theta 2, right? Just rotations. If I rotate by theta 1 and then followed by rotating by theta 2, that's like theta 1 plus theta. So from this point of view, multiplication is addition of angles. And it doesn't matter how you use that, right? There's an identity, which is rotation by 0. And then there's an inverse, which is rotation by minus theta. In this funny case, so the group, I just told you about the group as how it acts on the manifold. But in this case, the group and the manifold are isomorphic. They're the same. The group is S1, the manifold is S1.
And that's already a representation, no? I mean, when
I haven't said a single word about representation. This is just the action of a group on a set. The group can act on a set. So what's the simplest example of such a thing that you do know? What's the simplest group you know? There's got to be something.
Just like that.
Well, that's way too trivial. Yeah, Z2. Two elements, right? What are the two operations of it? Doing nothing, identity, or swap. The set has two elements. The group has two elements. So the group and the set that acts on are isomorphic. This is simple. As a matter of fact, there's a whole structure like that. I'm not teaching math here. All right. What's cool about this is that the word differentiable. What does differentiable mean? It means that I could do an infinitesimal group transformation, dg, d theta, right? But right, that's now these infinitesimal. What I want you guys to know this from this example, this innocent looking example, is that the infinitesimal translations, infinitesimal rotations, infinitesimal group transformations are generated using a vector tangent at that point. Right? So that is del theta. That's the generator of this guy. Right? It's a very, very simple example, but I want you to distinguish the generator and the group element. The generator is an element of the tangent space, right? This vector that moves you along. The group is the whole thing, the thing that transforms. Good? So the set of generators are going to become the Lie algebra, and the whole thing is going to become the Lie group.
So
yeah.
What's the difference between the infinitesimal transform and the
So the infinitesimal transformation is generated. Infinitesimal group transformations are generated by the generator. So there's a generator essentially. All I'm saying is that what's the difference? It's exponential.
Okay.
So if I view this as exponential rotation, this is e to the power of I theta. If e to the power of I theta is the rotation, that's an infinitesimal version would be e to the power of I d theta, because this infinitesimal is equal to 1 plus I d theta. The generator is that, well, no, I like. So, let's say rotation by theta 1. This is the group. The generator is when you take this, well, okay, so now take this to be infinitesimal. D theta, del theta, which is 1 plus I d epsilon. Let's put things to the epsilon plus epsilon d theta. This guy is the generator. So d theta is the generator, this is the group element. That's a very good example. I was just going to wait for a little bit longer. But the group elements are exponentiated versions of the generator. Now, there was a question about what do we need to talk about different Lie groups, and what kind of differentiable groups are Lie groups? Lie groups are the groups that you could exponentiate this guy and exponentiate these guys, and it will get you everywhere. Right? So the knowledge of the tangent space teaches you everything you ever wanted to know. Yeah.
When you said everywhere, like within a neighborhood?
In the group. No, not in the neighborhood, it's a group, everywhere.
Let's say that I like recover a group element by using the generator of the tangent space.
Yeah.
I mean, that can only generate the points that are.
No, I just look at this example. E to the power of, by exponentiating the generator, I can get everywhere. I'm exponentiating.
In what cases does that not work out?
That's a good question. You guys think about that.
It's great. It's great.
Anyone, do you want to say answer?
No.
Anyone has an answer?
It's great.
No, well, yeah, let's just talk about differential groups that are not leaders. What can go wrong? Well, there are a whole bunch of things that can go wrong. Yeah. Let me give you one bit extra bit. I think just about to move on. It might be that the tangent space, the tangent vector from point to point change. Right? So the Lie group is a nice setup where it's the same thing all over the place. That's why I can take the tangents and exponentiate it and get it everywhere. They're very, very symmetric. Let's go through a bunch of examples, all right? If you want to know what the definition is, you open up our and you read it. I'm not going to teach that. I'm not going to teach that, but I'm just trying to give you some intuition. Yeah.
But when you say the knowledge of the tangent space gives everything we need.
The whole group.
Yeah, but that's why is then the identity so crucial to find the Lie algebra?
But we'll get there. We'll get there. Yeah.
Just trying to understand the last point. Let's say that I have like, like a generator on a tangent space at a particular point on a manifold.
Yeah.
Right. And then let's say I want to find what is the group element somewhere far away.
Yeah.
How can I use the information on that point in that tangent space to get the information?
Here. You have a function on a circle, so you have a function f of theta, right? You know the value of f at theta 1. You want to know, and you have this guy. You have access to the exponentiation of delta theta. You want to know the value of it at f theta 2, right? What is the way to get it? It's e to the power of theta 2 minus theta 1 del theta applied to theta 1. This is the theta 2. Not I. There's no I in there. Yeah, there's no I. Just Taylor slash.
Why is there no?
Let's not get into that. Let's not get into that. Because I'm talking about the action on the real functions. What we're talking about Hilbert spaces. These are complex vector fields, so have to then either the generator has to connect. Remission, I like. One is a unitary representation, the other one is constant. This is not a unitary representation. All right, good. We're good. All right, let's go move on to the next example. So this hopefully clears up a little bit more. Now I'm gonna do something somewhat silly, which is to tell you. Now this is my first. The group is what I defined. I'm gonna give you a different representation of it. So the representation of the group I gave you, just colloquially speaking, was I represented. I haven't told you what I mean by that, but it colloquially, intuitively, I represented every element of a group by an angle between 0 and 2 pi. That was one way of representing the information content vector. Now that was a one-dimensional thing. You just had one number to describe an element, and it did one number. Now, what I'm going to do is I'm going to use a silly notation, perhaps, which is a different representation. This circle, I'm going to use xy's, right? And I'm going to represent the same concept. So now my group is a rotation that acts on two-dimensional vectors. Previously, it was just acting on an angle. So I was looking at the action of the group at S1. Now I'm looking at the action of the group on R2. Now the action of the group on R2, it's the same group, but it's a different representation. So representation is about what the group acts on. What vector space does the group act on? Building towards that, I will give you a definition of representation. But hopefully this is as real as it gets. This is the distinction between same group represented in two different ways, right? So G is always S1, it's always a circle. The matrix multiplication is the way that these representations work, right? Previously, we also had matrix multiplication, but it was one-dimensional matrices, aka numbers, right? Now, what is the infinitesimal element here of this representation? I just take cosine theta, sine, minus sine theta, linearize it, so this is d theta. Theta is small, it's epsilon. And this is the generator. The generator is I sigma 1 minus I sigma 1. Right? It's the same group. And the Lie algebra is that guy. Matrix multiplication, matrix exponentiation. I did not put an I. Good. Sorry, let me make one comment. I said exponentiation. I did not clarify, maybe I should have clarified this, whether I put an I exponent or not. That's a question of, are your generators, what's the nature of your generator, right? For now, I'm just exponentiating the elements. Yeah.
Maybe it's understood that, so we can say that all the representations are connected by different.
No, these manifolds, I mean, there's no nice connection between S1 and R2. They live in different dimensions. It's important, right? Like the representations could have different dimensions. Now, you're up onto something, but like it's way more deep into group theory and topology. Yeah.
You said representations are just, or are determined by what the group acts on.
What vector space the group acts on? Yes. I'll give you the definition in a bit if we get there. 245, right? I think I'm doing all right. Any questions so far? So this is your second example. But the second example is somewhat of a cheat. This is, I've only given you one example of a group, right? But this is not all that crazy, right? If we're talking about the action of Z2 on a group with two elements, what's a nice action of Z2 on a group with larger elements? Largest set of elements. What is it? Give me an example. Just like a simple, very, very simple. Multiplication by -1, action of it on real numbers. That's a Z2 group, right? It acts on real numbers. Or your favorite set of numbers that's closed under the Z2 action. Take a set, take your favorite set. Oh, whatever. If I go on tangents, you could stop me. All right, so now I'm gonna give you the first example, non-abelian example. The non-abelian example is rotations on R3. But the group is, the rotation on R3 is I'm describing the group in a particular representation. Once I give you the group in one representation, I've given you the group. Right? But I've given you more than that. I'm describing the action of the group on three-dimensional vectors. Right? So these are Euler angles. It's a three-dimensional group. I need three parameters to quantify it. These are the Euler angles. If you put it on next to my head, I will probably remember how to define these angles, but I always forget. So, but the important part is that the way it works is that the elements of the group, like previously we had a G, is a collection of three numbers. The representation is a map from those three numbers to a matrix that acts on R3. Right? In the previous example, the group was thetas between 0 and 2 pi. One representation was mapping this to one-dimensional matrices, I don't know, eta bar by alpha theta. Sorry. Another representation of the same group was this thing, cosine minus sine theta, oh, sorry, minus sine theta, sine theta. Right? So it's always a matrix. This is one-dimensional matrix. It's always a matrix. So here, the matrices are the rotation matrices, the way that you represent them. Right? Now, this is non-commutative. It means that G1, G2 is not the same as G2, G1, and the matrix multiplication will have to manifest that. So group is some abstract beast representation, you know, just like puts your feet on like firm ground. Right? It is what it is, it's a representation of the group. The group is very abstract. And you could admit all sorts of different representations. Probably you're from quantum mechanics, remember SU2. Then it's all sorts of different representations. Good? All right. Now, you have more than one generator, right? The generators live on the tangent space of the rotation group. They form a Lie algebra. Oh, yeah. They live on the tangent space of G, right? Tangent space of G. It has nothing to do with the vector space it acts on. Right? That would be a representation of the Lie algebra. I have the Lie group. There's an abstract object. There's a Lie algebra, which is the tangent to that group. Now you have a representation of the group. It also automatically gives you a representation of the algebra. This exponentiation tells you that the representations are exponentials of each other. Yeah, one of them is exponential. Yeah.
But the algebra is independent of the vector space, which is to which the group acts.
Yeah.
Then why is the structure constant of the D?
Oh, yeah. So the structure constants are. What was the question?
I mean, the structure constant really has a notion of dimension of the.
They're just abstract.
Okay.
They're just.
They also
algebra.
depend on the.
It's crucial that they do. Crucial that they not. Otherwise, it would be silly to even talk about. Anything that depends on the representation is you will not hear over and over and over again. Right? Like if you repeat those words, it's because it's fundamental group theory. All right. Good. All right. So what is the tangent space here? As I said, I don't remember how the Euler angles work, but I actually sort of do. If you give me Mathematica. So this is X3. This is the generator. We call the generator of this rotation, right? This rotation, the generator, this was exponential schematically of this thing. what was that? Minus theta theta 0, 0. Right? So it's pretty easy. I have a three-dimensional space and the three rotations are independent. So I take this guy that rotates, that keeps the z-axis fixed, exponentially this guy. I take this guy that keeps this rotation around y-axis. I take this guy that's rotation around x-axis. I exponentiate them, multiply them. There you go. That's your Euler angles.
There shouldn't be a one there, right?
There's a one.
I mean,
Yeah, there's a one. There's a one. Yeah, there's a one. Sorry.
Like it should be zero.
Correct. Of course. Oh,
Like zeros instead of.
no.
There.
No. Yeah, no. That's correct. Sorry about that. Yeah. So now these are matrices. In a particular representation, you could check that they satisfy that algebra. Here's a wacky one. It's not wacky. From a condition to triviality. It will just go crazy with the matrices worse from physicists. But the commutation relations, these are Lie algebra properties that exist abstractly. No matter how you represent your matrices, those commutation relations will always hold. That's why Lie algebras are so nice. Lie groups are so nice.
But there you see the structure constant. I mean,
And I said it's independent of the representation.
I mean,
Yeah, those relations are independent of representation. That's exactly what my point is. My point is that these relations, the commutative Lx, Ly, Lz, those are independent of your representation.
So,
No matter what matrices you use to represent them, those will always hold.
like for differentiable non-Lie algebras, you basically.
No. Like the whole thing goes. Yeah. It's Lie algebra structure in mathematics is sort of like there are actually literally there are these results called rigidity theorems, which is you can't take the structure of Lie algebra and generalize it. Lie algebras are very, very, very solid. Like another way of talking about this is that so they often correspond to symmetric spaces, like S2, which is symmetric, and never with a canonical metric, right? Round metric. But how would you have something that's almost symmetric? You can't have that, right? So you need extra data. Like it's either symmetric and nice as characterized using the tangent space at every point, or it's not. There's no in between. I was gonna make a bad joke. All right. Linear representation. Now, with that all said, now I can actually define what a representation is for the purpose of this course, for the purpose of anything any physicist ever does. As we talk about linear representation, it's a map from group elements to matrices that I represent with R. So G is sent to R of G, such that the group multiplication is matrix multiplication. Done. That's the definition for you. Right? So this definition, you have to unpack it. When I say it's represented as matrices, I've told you what the matrix, what the space is that they act on. Right? It's the dimension of the R of that. It's a vector space where the matrix act. So now a physicist, when they talk about representations, they might jump around actual representation as well. Sometimes by representation, they mean the vector space that it acts on. Sometimes they mean literally the matrices. Doesn't matter. They're the same, right?
And it has to always be matrix.
Matrix, always. Why actually?
Is the vector space is used.
It's a linear and it's associative. The linear and associativity sort of force this matrix multiplication. Yeah.
given a Lie group, do you have any restriction on which vector spaces can it happen?
Sorry, say it again.
So you have a Lie group,
Oh, that's called representation theory.
but you have restrictions. Like,
That's called representation theory. The main question of representation theory is this. I give you a group. Tell me what are the vector spaces it can act on. What are its representations? That's called representation theory. Now, representation theory, as I just explained it, there's not very, there is a systematic side to it. But the very, very systematic thing is if the magical words are these representation theory of Lie groups, that's magical because it's a done deal. Mathematicians have finished this. It's understood, it's all works so well. It's one of the yeah. You should be shocked. I can't tell you should be shocked, but it's a shocking statement that I can list all the Lie groups here. All of them. Modulo some subtleties. So what is a subtlety? If I take two Lie groups, take two representations, and put these blocks like in diagonal matrices, and I can just trivially direct sum, right? So modulo those kind of subtleties, they've all been classified as such. Sorry?
What was the last part?
That they all have been understood and classified. So
Oh, okay, gotcha.
have been understood and classified.
Does that mean there's like a finite set of symmetries? Finite set of differentiable.
Nice symmetries.
Yeah.
No, but there are also finite groups. Right? There are finite groups or discrete groups. You'd be if a discrete group has finite number of elements, they have also been classified and understood. That's one of the. It's even more impressive than the other three groups. That's a really crazy thing. That we know all the finite groups, all of them.
Wait, so there's a finite set.
So these are where the group is a set of like it's a finite set G1 to something. And really wacky, okay, I'm running out of time. Is that there exists a largest finite group. That statement should blow your mind. There exists such a thing. It's called the monster group. There exists one largest finite group. That's 2 times 10 to the power 71 or something elements. But nothing is larger than that. It's larger than that must be. All right. All right, good. Now, so what are the examples? I'm gonna build on the examples and give you more examples. Rotations in Rn. What is it? The group is called On. I'm giving you a representation of it, right? But there are various ways to talk about it. It's called On because it's orthogonal n by n matrices, right? Orthogonal means that your rotation, your representation matrices R satisfies that equation. R transpose R is equal to R transpose equals identity. Right? So what are these? What's the physics of these transformations? Think of the vector of a bunch of fields, right? And these are rotations. If these are real fields, this could be rotations. This is a generalization. So this is not a rotation. I think, sorry, I apologize. This is not a rotation. They include rotations. Do you know what else it is? Oh. All right. They preserve another way of defining. They notice that they preserve the following thing: phi transport. Yeah. So this is the vector space representation axon, right? Rn, and sometimes we say the representation is Rn, right? So this, what it does is that these R's preserve phi A, which is phi transpose phi. This is saying that there is an inner product or metric that it preserves. What is that metric? 1, 1, 1, 1. Now it should look familiar from Lorentz group and all of that, right? So it preserves these guys. Now, the fact that the R transpose R has to be 1, it means that the determinant of R is either +1 or -1. You need an example for that? You could mod out by 2 with Z2 and consider the set, the group of ON matrices with determinant 1. This is called SON. So ON is always twice larger than SON. Now, interestingly, ON is disconnected. So I lied to you when I told you that you could start from any point and get to any other point. Right? By multiplying, by exponentiating the tangent vector, you could never change the determinant of the vector. Sorry, you can never change the determinant. So there are two disjoint components to it. One of them has determinant 1, the other one has determinant -1. So that structure is allowed as well. That when I was trying to build intuition for you guys, what I meant was that if it's a connect. Good?
That's with ON being the algebra, it cannot be the algebra.
As a Lie algebra, it's very complicated algebra. Sorry, ON is a Lie group. There is a corresponding Lie algebra. So notation-wise, Lie algebras are often written with small things. So for example, if you have a ON, I don't know how to represent a little ON, right? And yeah, that's usually, or SON is like SON. Want to know what this is math fact. That's what the answer is, math fact. All right, yeah.
When you say the groups need to be connected, why not?
No, I never said that.
But if you want to,
I said I lied when I told you can get from any point to any point.
but
The Lie groups don't have to be connected.
okay.
Don't have to be connected. So ON is a Lie group and it has two disconnected components.
SON is correct.
ON is connected.
SON.
Sorry, SON is connected. Yes. What is SON, by the way? As a manifold. What is SO2?
It's for the measurements.
You just saw what the SO2 is. S1. I just gave you the example. Yeah. SON is an n-1 dimensional sphere. It's Sn minus 1. So S1 is SO2. What is SO2? Just cosine, cosine, sine, minus sine. That's SO2. Well, what's the representation? So it's always a sphere. So sphere have one connected component. So if you want to imagine SON, if you want to imagine ON, imagine two n-1 dimensional spheres. Now, one comment, I'm not sure if you will this. I think as a physicist, it's my responsibility to make this comment. There are two notions that appear here. How many disconnected components do we have? Keep that in mind. Now, let's focus on the connected part, all right? The connected part might still be not simply connected. Simply connected means that every 2 points could be, there's a path between them, right? It's possible that it's not simply connected, and that is dramatic in physics. So, two notions we're going to deal with: connected, or how many disconnected elements we have, and how many different, like whether things are simply connected or not. This is crucial for a representation to this one. Good? Yeah, just 1 second. Yeah, go ahead.
Now this just tells you what the whole is. The group is, right?
One-dimensional holes. So this is homotopy groups, and it's about. All right, good. Any other questions? So I defined ON and SON. Now, let me define a couple more, and then I'll stop, and then we'll be, you'll have seen all the lead groups that you will probably need in your life, except you deal with exceptional groups.
I guess all the lead groups are simply connected.
That's crucial. We have fermions in nature, we have spinors and fermions in nature. That's a consequence of the fact that SO3, 1, which is the Lorentz group, is nothing. All right. We'll see that. We'll explain what the hell is a spinor, all of that. All right. So a couple of more groups. SUN. This is a simple generalization of ON, where I'm going to describe it as unitary matrices that act on a Hilbert space. Well, Hilbert space is an inner product complete complex vector space. So instead of it acts now on phi1 to phi n as a vector, but these phi1 to phi n are complex vectors, right? And then, of course, so now it preserves the inner product of that vector space, right? And it will be u dagger u equal to u dagger equal 1. It leaves phi dagger dot phi dagger phi in there, right? Very good. Now, what is the determinant of u? Previously, because we were dealing with the real matrices, there were two choices, +1 or -1. Here, it could be a phase, right? So we could talk about matrices, unitary group of matrices, group of unitary matrices with determinant 1, and that's called SUN. And by n, unitary matrices. What is the X? So previously we had two copies of it, +1, -1. Here we have an extra phase floating around. E2 parallel out.
So we have infinite copies.
Sorry?
We have infinite copies. UN has infinite copies.
No, I didn't say that. You mean connectedness? I didn't make a comment about connectedness. I just wanted to say that it's natural to consider SUN.
SUN is just UN modulo S1.
Modulo S1. Okay, so now Lorentz group. Lorentz group is also the same beast. Lorentz group is the thing that acts on RD, 1 vectors, right? Or another way of describing is that, what was the orthogonal group? So O of n preserves this. O of n minus 1, 1 preserves this full silence. That's your Lorentz group. Done. Good. So that's OD, 1. Now, so for examples would include, so these are Lorentz transformations, right? So now lambda transpose lambda is identity. We end up with the same situation. Now the determinant of lambda has to be what? Either +1 or -1. So there are two options. I can pick the one that has determinant 1, and that's called SOD, 1. What is the symmetry of nature? Is it O3, 1, or is it SO3, 1? You guys know?
S. It preserves time reverse, right?
It's not SO. It's not SO. Well, we'll talk about that. It's a subtle question I'm asking. By the way, there's no way to know a priori. You have to do experiments. There's no way that ancient Greeks could sit somewhere and just answer how many teeth does the horse have, or what's his space time. There's no way to know, right? Yeah.
Is there any group I guess just like when you choose determinant because you want to have S, you just add S, right? Just to separate that. What do you have to do in negative one? What consequences Like what? How different would that be?
It's just, yeah, I don't know, like there are, the case of, think of an ON, it's two disjoint ones, right? Which one I define to be the determinant one doesn't matter. The two components are isomorphic. From the abstract group theory we're thinking about it, that this group has two disjoint components that are identical, that are isomorphic, right? Whether I pick determinant 1 or -1 is my choice of convention in different dimensions, whether I pick -1 here or what. That's the statement of a representation. Recall, like the group that has two disjoint guys, and that's something you could ask and answer. Oh, okay, sorry. Oh. Yeah, I'm on slide 10 out of 17. All right. Oof. Let me regroup. All right. So I lied when I said I'll give you all the groups that you need for today. Somehow I went through this last year. Okay. Anyway. So what is so many representations of a group? A group representation is a map from R to RG, where RG is a matrix and it acts on a vector space. A group can have many equivalent representations. Another example. So example here is SU2. It acts on two-dimensional vectors, right? Complex vectors, a Hilbert space, 2D Hilbert space called qubit. What does it preserve? The inner product of the Hilbert space, right? So it preserves the inner product of the Hilbert space, and this group is, what's the dimensionality of it? It was a trick question. The dimensionality is associated with representation, not the group. This representation is how many dimensional? 3-dimensional. Right? How do you yeah, so you need 3 generators. Right? Or if you want to think about the vectors, these are complex vectors that are unit norm, right? So there are 3 independent vectors. So sigma x, sigma y, sigma z. Now, very quick question. So this is a representation that has, okay, it's a particular representation. Let's take the word back for the quick question. So take SU2. Paul from quantum mechanics will recall that this could act, this representation could be classified this way. So this is the first funny result. I'm listing a whole bunch of representations. They're labeled by number, S, right? Spin 0, spin half, spin 1, spin 3 halves. Then, okay, these are numbers. Each of these guys, there's a vector space, which is a representation that has dimensionality 2s plus 1. There exists no representation that is. No, I didn't say that. All right. So what are these representations in arbitrary dimensions? Arbitrary 2s plus 1 dimensions. They're generated by J plus J minus and JZ that act in the following way. These are the raising lowering operators that's you're familiar with. It's the same damn group, different dimensional representations. Right? Question.
Don't we not have n equals 0 when S is a happen?
That's a trivial. S equals 0, you said? That's a trivial representation. It's a one-dimensional thing when all the matrices are identical.
No, I mean when S is a half integer, you can't get n equals 0.
M equal. Oh, sorry. There's a that. Yeah. This is not. Yeah. Thank you. All right. Okay, I'm out of time and I don't know what to do. This is depressing. All right, we got to stop. All right, let me okay, let me at least summarize. Yeah, we're running out of time. I don't know what to do. Yeah, so in summary, what was I talking about? We talked about groups. We talked about symmetries forming groups, right? We argued that. Symmetry is an abstract thing, but in physics, we want to talk about this representation, right? And yeah, I guess we talked about Lie groups and Lie algebras. We didn't talk much about the algebra. We'll talk in detail about them. They are differentiable symmetry transformations with some extra properties. That will, I think I might actually include the definition at some point because it seems like we always have plenty of time. So, all right, good. I think that's my 1 minute summary of it. Are there any questions? If not, thank you so much, guys.